So now let's start with the function optimization. So what we do usually when we want to do model training, we typically do it. We're going to end up with such a problem, right? Well, we're going to have a bunch of data samples, x's and labels, and then we're going to pass those data through the model. We're going to see some output. So this f of x is going to be your output. Probably you had a bunch of hyperparameters. You already said it. And then you have a bunch of weights. And this is what you want to just find, right? So what you can say this whole empirical risk that I'm looking at is actually a function of the weights, right? I mean, could be a huge number of weights, but at the end of the day, it's a function of those weights. And the thing that you want to do, you want to just minimize that function with respect to the weights, right? So here f is general model, but in deep learning, we typically think of it to be a deep neural network. Then this h is essentially the hyperparameter, which is specifying the architecture. And this w is just containing the weights and biases, right? So you have one function, which is a function of all of those weights and biases, and you want to minimize it. You want to find the set of weights and biases that make this function minimum. And x and y, of course, they are the samples that you have inside your data set. Now, L is also the loss function, that's right. But at the end of the day, what you want to do, you want to just solve this minimization, right? And you might say that, even getting into that expression, that empirical risk is looking super complicated. But right now, forget about it. We're going to talk about backpropagation with too much details that you're going to just hate me at that point in the next chapter, OK? So right now, you don't think of that, right? You just think of one function. First thing that we want to know is that is there any sort of machinery which going to help us? If I have a function and I'm able to compute a few things out of it, is there a way that I can algorithmically find the point which makes this function small, right? So now, we are going to look at this function. So for us, this is the empirical risk. But right now, as I say, you just think about any function. So I give you a function. You want to just find the point which is making it minimum. And when you have a function, you have two types of minimums or optimum points, right? So it could be a global minimum. It means the point which makes the function globally minimum. There is no other point, there is no other choice of weights w, which makes this function smaller, okay? This is what we call a global minimum, right? So here what I'm showing you is a one-dimensional function. I'm assuming my model has just one single weight, right? So in practice, this function is not one-dimensional. It's huge dimensional, right? So it's crazy large, but we cannot draw it here. So this is why I'm showing it like this, right? And now, this is what we call a global minimum. You could have also a local minimum, right? You could have a point which is smaller than everybody around it. But when you come out of the neighborhood, then you find some other points which are smaller, right? So this is what we call it local. Of course, we would be super happy if we end up with a global minimum, right? So that is the best choice we can think of. But the key point is that in practice, we're not going to get there. So we usually are happy when we are ending up with a local minimum. Because at least with respect, in this neighborhood, as compared to everybody around, we are doing fine enough. OK? So now, the question here is that how we can do it algorithmically. Is there any algorithmic approach? And I do know that probably all of you don't think like that. But I'm just, as I said, I just consider myself as a reference. As a kind of naive, stupid person, when I were in your situation, I would ask this question. OK, why should someone really care about this minimization or optimization problem so much? Why everybody is obsessed with the problem of optimization? So look at this function. This is one axis, right? So how bad it could get? Let me just grid it, right? And then I compute the function at every grid. And then I see where the function is small, right? Wherever it's small, that should be the right neighborhood, right? So I go and search a bit inside that. I approximately find the point which is minimizing the function, right? You might think like that, but the point here is that you're just thinking about one single parameter here, right? In practice, you have huge number of dimensions, right? So let's say, for example, I have d different dimensions. It means that that vector w is not just one weight, it's d different weights, right? Now, if I have one axis, if I have one axis, so this is the first axis w1, when I want to grid it, I'm going to have one specific resolution, right? If I have a couple of points, right? For example, say I put 10 points here, right? Now, the key point about these points when I'm doing the gridding is that the distance between these points is small, right? Now, if I have now 2 dimensions, so w1, w2 now, right? If I want to have grid points, the grid point should be somewhere in this space, right? In this plane. And now, if I want to keep the resolution the same, it means that every single pair of points are being distanced as before. They are as close as before. How many points do I need? I told you 10 here, right? 100, right? So I have 10 points here, right? I need to have 10 points here as well, right? And then the number of 10 grids here, 10 grids here. And I should consider every single point that is on the cross-section of these points, right? Anybody that is on the cross-section, I should consider it, right? So I have 10 here, 10 here. The number of points in the plane is now 100, right? What if I go for the third dimension? What's going to happen? It's going to be 1,000. If I go for d dimensions, how many grid points do I need? 10 to power d, right? Now, if you, in general, you would say that I am doing this gridding with g different grids on every axis. To keep the resolution the same, it's not that you are improving it. You're just keeping the resolution the same. Like the distance between the points that you are checking is the same. You need to have g to power d, right? And this is exponential growth. This is what we call it curse of dimensionality, right? When things go linearly large in dimension, the surge that you need to do is going exponentially large, right? And you can never, ever handle it, right? This is one of the highest order of complexity you can think of. For instance, say that you have a neural network with 100,000 parameters. Is it so weird? No. I mean, like the simplest neural networks that you can think of right now have much more parameters than this one, right? Now, think of only 10 grid points, not even larger than that. Then it's going to be 10 to power 1 5 zeros, right? How much time you need to search that? Just go ahead. Think about the the fastest computer in the world. At the end of the day, you're going to end up with 10 to power 900 something century, which means that more than the age of the universe, right? Like the whole universe has been I don't know, 10 to power 14? What is it? The number of years, right? So it's even more than that, like more than the time from Big Bang. You can never do it, right? So it's true that in theory, you can say, oh, I grid and I check those points. And this is very good to think like that when you want to imagine or visualize things for yourself. But you should always take into account the computation that you need. And this is something you cannot handle, right? This is why people are obsessed with optimization. This is why optimization is a one line of study in math, right? Now, what we want here in this course, we want an optimization algorithm, or what people usually call it optimizer. So what is an optimizer? This is one algorithm which is going to start from one initial point. That initial point is randomly chosen, right? So you're going to just start your neural network with a bunch of random weights, right? And then you want to have a mechanism that you start looking at this point, you do a bit of computation, feasible computation, not super complicated, feasible computations, and then you understand how you should fix those weights, right? You change them, right? And then once you got the new weights, again you repeat this, and you keep on doing this till you see that your empirical risk is actually minimum, right? So this is what we want. So we want to start from one initial point, and then we want to just do multiple steps, right? And in every single step, we want to just look at our empirical risk. We do a bit of computation on that function, simple for computation, not super simple, but at least feasible, something that we can do with our computers. And then once we have done it, then we get an idea, maybe we should change a bit of these weights in this form, right? And then we change the weights, and we keep on doing this till the function gets very close to the minimum, right? And we don't want this number of steps also to go to infinity, right? We want to approach to that minimum point in a feasible number of steps, right? 100, 1,000, it's okay, but it should reach to that point, right? It should not take forever, right? Everybody's clear? So this is optimizer, and if you can come up with any algorithm that does this, you are designing one optimizer, right? But the kind of optimizer that nowadays everybody's using is the one which work by gradients, right? By derivative of the function. And what is the reason? We're going to see why, because derivative are actually giving us idea where we should move to. Okay? Everybody's cool? Questions? Yeah. I mean, if you know that function has a bunch of properties, we're going to mention it, then you can guarantee that you are going towards global minimum. But in practice, the functions that we deal with never have those properties, and we never end up with that. But that is not an issue, because we are still happy when we get to a local minimum. You're going to see it later in the course. You're going to build some intuition on that. But like in a nutshell, when you have a super complicated neural network, then you're going to have lots of those local minimums. And you have so much of those local minimums that all of them are as good as, say roughly, as good as a global minimum for you, right? So, and then you're going to stick to any of them, that's fine, right? So when you overpromise, right, like you have a huge neural network, this is going to eventually happen. Questions? No question? Okay, so if you got no question, then let's just write down the optimization algorithm. So the optimization algorithm is supposed to start from one weight point, right? Some initial point W0, right? Forget about delta right now. Don't think about this. So I start from 1 W0. Once I'm at W0, what I want to just look at my function R hat, the empirical risk that I have, right? I use this function to find out some moving direction, right? So I'm going to say that I have W0. Maybe I put it inside this function. I do a bit of calculation. And then at the end of the day, I would say, OK, this direction mu is the right way to go, right? Once I find that direction mu, then I am going to update my weight with that direction mu, right? So I'm going to say this is the right direction to go. If I go this way, my risk is going to get smaller. And then I start to move in that direction. It means that I get the previous weight. When I am in the first iteration, I'm going to get W0. And add up this direction, and I find the new one, right? Now, when I found the new one, I want to make sure that the new one that I have found is good enough or not, right? And to find it out, I would say, OK, this new guy, I compare it to what I had before. Like, before updating, the loss was something, the risk was something. After updating, the risk got something else. If it's not changing, so maybe it means that my algorithm is not doing anything anymore, right? So I should stop. So this is what I call a delta. So the difference between the value of the function in different steps. And then I'm going to compare this delta to one tiny threshold. Maybe that threshold is 10 to the power minus 10, right? So when I see that the function is not changing, I would say, OK, probably I should stop here, right? Now, this algorithm, you can apply it pretty much to many things, right? Anything that you want to find, any search algorithm in a continuous space, you can do it in this way, right? The only question here is that, how can I find out this mu vector? How can I find the direction that in each step I need to update my weights with, right? And a little bit of a spoil, you do know what that guy is, right? That's going to be the minus gradient of your objective function. But we're going to see why this is the right direction, right? So what intuitively we want to happen here in line 5 here, each time that we are doing the update, we want that roughly, not all the time, but roughly most of the times, the function is going to drop, right? Because if the function is going up, it's not minimizing, obviously, right? If the function is just going up and down always, it's not minimizing again. We want this guy to just go down, right? It's OK, it goes a bit up and then goes down in practice. That's fine. But we want to have a kind of envelope which is going down, right? This is one thing that you want. And the other thing is that you want this to happen in feasible number of iterations, right? You don't want to have this delta never getting small, right? You don't want delta to be large forever, because then your algorithm is going to run forever, right? So these are the two factors that we want to see. And the key point here is that we're going to see that when we put mu to be proportional to the negative of the gradient, we're going to get both properties. Like that direction is going to reduce the function each time. And at the same time, it could put it, when we get close to the minimum, then going to get close to 0, then our function is not going to change anymore. Questions? No question? OK, so now this is the general optimization algorithm. And now we're going to make it to be gradient descent later when we just replace this guy with the gradient. But the main thing that I need to just clarify here for you is that why we need to put it to be minus gradient, right? Once you understand it, then the rest of it is clear for you. Now, I do know that it might sound a bit very basic because I'm just getting back to derivatives. But I just want to give you the intuition, how you should think about derivative when you are dealing with training problem. So excuse me if that is too simple. I do know this is high school. But just to recap what that means and how you can think about it, that is the more important point. So now, derivative of a function. You do know the definition, definitely, right? Each time that I show it, the student's going to complain, come on. I know you know it, right? But let's think about it once again. So if I am at one particular point, w0, and I want to compute the derivative, you can use any of these notation. You can write it f prime, d to dw. You can write it f dot. All of them are derivative. That's fine. Now, if you are computing this derivative, you're going to compute your function at that point w0, right? And you add a tiny bit to the w0, right? A tiny delta. And then you see how your function is going to change from that point to w0, right? And then you normalize it with this difference, right? And then you make that difference small enough, and then you say this is the derivative at that particular point, right? So now, how we can think about this guy, we can say that if I am changing w at point w0 with a very tiny step, which I'm showing it by dw. So this dw is essentially the small version of this delta here, right? If I just take the tiniest step dw, so I'm here, and the smallest step I can take towards, forward in the axis. So on this graph, the forward direction is this, right? So if I take the tiniest step, then as long as I am on the function, I am going to go up or down, right? Because when I'm walking on this function, when I take a tiny step in this direction, I might just jump up, right? It's a very steep mountain, for example. Now, the derivative, what it's showing you is telling you if you know this tiniest step, how large it is, you can approximately say how much you go up or down, right? So what I can say, if I get w0 and I just move tiny bit in that direction, then on the graph, I am going up, right? For example, in this particular diagram, right? And the ratio of this going up on the graph to this step size that I have taken, this is going to be your derivative, right? And this is consistent with the intuition you had. This is the slope that is just tangent to the curve at that particular point, right? This is cool, right? Now, but having only this intuition is going to help us build idea how we can move towards the minimum or maximum of a function, right? So how we can do it, say for instance I have this function. First of all, let's see what kind of property the derivative has. So here I am moving in this direction, right? So I'm moving to the forward direction on the axis. And then the derivative here, what is it? Is it positive or negative? What is the derivative? It's positive because your function is increasing, right? dy is positive, dw is positive, so derivative is positive, right? So derivative is positive at this point. This means that if I move in this direction, in the forward direction at this point, what's going to happen to me? I'm going to increase in function, right? So the thing here is that the derivative is positive. Then this means that if I move in this direction, so the direction that derivative is telling me is positive, go forward, right? When I go forward, then the function increases, right? Clear? Now, what about this function here? What about, at this point. The derivative is negative because when I just move forward, then the function going to drop, right? Clear? The derivative is negative. The slope is negative here, right? And now, derivative is negative. What's going to happen if I move forward? The function is going to decrease. But I can interpret it the other way around. I would say the derivative is negative. Now, this is the positive direction. If I want to increase my function, what should I do? I should move in the direction negative, right? Which is the direction of the gradient, right? The derivative, right? So what I can conclude here is that this sign of the derivative in this one-dimensional function is telling me the direction that I should move to increase the function. Now, if instead of increasing, I want to decrease the function, what should I do? I should move in the opposite direction, right? So, for example, here in the first one, I want to decrease the function. Then at this particular point, I know that derivative is positive. This means that this direction is the direction where the function is increasing. So I'm going to move in the negative direction, right? But in the other point, the gradient is negative. So negative is the direction that function increases. So I move forward to decrease the function, right? So key observation here, if you think of derivative, sign of the derivative, the direction on the w-axis, right, to which you can move is either positive or negative, minus that direction is going to be the direction that your function is going to get smaller, right? OK, that's cool. Now, can derivative become 0? Can it be 0? Yes. Where can it be 0? Minimum, maximum, and inflection point, right? Inflection point, we're going to see it. Now, this is when the function is maximized, right? Now, if the function is maximized at that point, you see that the derivative is obviously 0 because the slope is 0 when it touches it. But now, let's do something else as well. So I just want to give you a bit of intuition here. So what you have here is your function, right? F of w, right? I'm going to draw w again here. And then instead of f, I'm going to draw f prime of w. OK? Everybody's cool? Now, when I start before w max, and I'm going forward towards w max, what is the sign of derivative? It's positive, right? Because the function is increasing. So it's positive, but the value is getting smaller and smaller, right? Till you get to the top, right? At the top, it's going to be 0. What's going to happen after that? It's going to flip the sign, right? It's going to get more and more negative. Now, here at this point is W max, okay? And now, when I am before W max, what is the sign of this guy? Positive. And what is the sign after this guy? It's negative. And at this point, it's 0, right? It's something like this, right? I mean, I'm not showing the exact diagram, but it's going to look like this, right? Now, what is the derivative of this guy at this point? If I take the derivative of this derivative function, what it should be? Is it going up or it's going down? It's going down. So what should be the derivative? Should be negative, right? It's going down, right? So what you can say is that you start from something positive, some positive derivative. You get to 0, then you start to drop down, right? Again, get negative. And this means that your second derivative is going to be negative. The derivative of this guy is going to be negative at that point, right? So if your derivative is 0 and your second derivative is negative, then that point is maximum, right? You can do the same thing for minimum, right? You could say that Well, if I am at the minimum point, then I start from some, what is the sign before, sign of the derivative before? Is negative, right? And I'm just moving because I'm just going down, right? Now, when I get this negative value start to increase up to the point that it gets to 0. What's going to happen after 0? It's going to increase, right? So if I want to draw the derivative function now, how does it look like? So I'm going to replace this W max with W min. So I have W min. And now, before this, the derivative is negative. At this point, it's going to be 0. And after that, it's going to be positive, right? So what is the second derivative here? It's going to be positive, right? So if you have your first derivative 0 and the second derivative is positive, then you're going to have a minimum, right? So you can always use this intuition that the direction of derivative is the direction of increasing, or minus derivative is minus the direction of decreasing. You can always use this in order to find conditions where your function is, for example, maximized or minimized, right? And you could have, for instance, inflection point, right? So what happens in this inflection point? Can you tell me, just before I explain it, can you tell me what's going to happen to the second derivative, for instance? It's going to be 0, right? Why? What's going to be the derivative before the point? It's positive. It's going up, right? So the derivative is positive. What happens to the derivative at that point? It's 0. What happens after that? It's again positive, right? So the derivative is positive. It comes to get 0. Then it again goes up. So what should be the second derivative there? It should be 0, right? So if you compute that, like it's just going up. It gets 0. It again goes up. So it means that the second derivative is going to be 0. So you don't really need to memorize any of this. You always can find it out by thinking about, just imagining that the derivative is just guiding me towards the direction that I increase, right? Everybody's cool? Questions? No question. Great. So if you got no question, then we can actually extend this idea to a more realistic case where we have multiple parameters, right? So you have multiple weights, so say W1 to Wn, and then if you think of that as a multi-variable function, then you can define what we call it the partial derivative. Now, I am pretty sure that all of you know what partial derivative is, but again, just to make sure that we are all cool and on the same page, so let's say I have this function. So I have function f of W1 and W2, okay? Don't we have a better chart? So this guy is, say, W1, W2 plus W1 squared, okay? What is the partial derivative of f with respect to W1? What is it? It's going to be W2 plus 2W1, right? So you're going to treat W2 as a constant, and then you take the derivative, right? Now, what is the partial derivative of f with respect to W2? W1, right? Because here we have W2 as a variable, W1 is the constant, the derivative of this guy is W1. This guy does not contain any W2, so it's going to be, the derivative is going to be 0, right? Everybody's cool, right? So you have the idea. Okay, cool. Now, if I have an n-dimensional function, how many of those partial derivatives I have? N, right? So I have Wn dimensional. The number of partial derivatives that I have is n, right? Everybody's cool? Now, the question is that how I can interpret these partial derivatives in the same way that we did it in the single variable function. Again, you can say that if I am like in two-dimensional space, here is W1, here is W2, right? Now, the point is that I can move in any direction here, but if I wish, I can fix one axis, right? I can just don't move on W1, just on W2, right? I take a tiny bit of a step in that direction. I want to see what happens on the function, right? Same thing to W1, right? I can move in this direction only. Now, if I want to move in general, but it's still a tiny bit, I can move like this, and this guy is going to contain a tiny bit of W1, tiny bit of W2, right? So what you can say in practice, you can say that in general, when I move in the n-dimensional space, I am moving with tiny step in every single direction, right? A point here in three-dimensional step, if I just tiny bit change it, every coordinate is going to change with a tiny bit of step, right? Clear? So these tiny steps are the values that I have moved towards in every single direction, right? But I actually, at the end of the day, moved in this three-dimensional space, right? Now, the question is that when I did this move, how much the function got changed? And how can I compute it? I can just extend the same idea as before. So I could say, I get the first partial derivative, and I multiply to the tiniest step in the first direction, right? I get the second one, multiply the tiniest step in the second direction, and so on till the last guy, right? So I moved tiny bit like this. This means that I have moved like this in this direction, right? And this in this direction, right? I take this one, multiply it to the partial derivative of the function in this respect. Take this one and multiply it to the partial derivative in this respect, and I add them up. This is going to tell me how the function changes when I move this direction, right? Everything is tiny still, right? Those dw's are all very tiny, right? Everybody's cool? Questions? OK, so I can write it down in this form. It's going to be summation of partial derivatives times the tiniest steps in every single direction, right? So I can write it down in this form. Can I write it down compactly? Is it any specific form of product you can remember? It's the inner product, right? So there are two vectors getting inner producted. One of them contains dw's, right? Which was defined here. This is dw's, right? What about the other one? What are, sorry? The derivatives, right? The partial derivative. The other one contains all the partial derivative. This is what we call it gradient, right? So you can write it down in this form. So you can say that I have this vector which contains all the partial derivatives, and this is getting inner productive with this tiny direction vector that I have, and that vector is what we call it the gradient of the function at that particular point, right? Everybody's cool? So this nabla f, this is the gradient of f, right? Now, what is the dimension of the gradient? Same dimension as your variable, right? Your function f itself is a scalar, right? But when you take the derivative, you take the derivative with respect to the first parameter, second parameter, third parameter, till last parameter, right? So always the gradient is of the same dimension as your variable, right? So it now rings a bell, right? We wanted that mu to be of the same dimension as our variable, right? And the gradient is looking like that, right? Everybody's cool? Questions? OK. Now, if you got no question, then we generally, from now on, always think like this, right? So if I have a function, and this function could be crazy high dimensional, I don't care. I take a gradient. You inner product that inner gradient with a tiny bit of movement. It's going to tell you how much your function is going to change, right? Cool. Now, if you want to think about it in visually, you can think about it like this. So here we have two dimensions for w. So w can be moving in direction w1 and w2. So in general, any point in this plane is now a feasible point to move towards. And you can choose any direction, right? And your function is going to be a surface now, right? So the value is at every single point you're going to have a value, so you're going to be a surface in the three-dimensional space, right? Something like this. And now, if you want to move, maybe you move a tiny bit in this direction, right? So you're going to say that I'm moving in this particular direction. Now, if you think of this vector, you can, of course, say that this guy is actually having a part on W2 axis, a part on W1 axis. And if you get these parts and you multiply them with the corresponding partial derivatives and you add them up, then you eventually are able to say how much your function is changing here, right? Everybody's cool? So you're eventually going to get your gradient. Your gradient is going to lie in your W space, right? Because it's again a two-dimensional vector. You can plot it in the same space, right? And if you inner product this guy and this guy, so this gradient and this dw, you get them, you inner product them, then you're going to know how much your function is changing. Everybody's clear? Questions? No question? Yeah. Sorry? Yes, the function, the surface of the function. Yes. So you actually are looking for this point. You want to get to this point. Like these are the weights, right? Weight 1, weight 2, right? If you change them, the loss is going to change. So loss is going to be a surface, right? And then you are looking for the point in this W space which is going to hit the bottom of the surface, right? So this is what you're looking for right now. Loss is the surface, right? If you choose any weight in your model, then the value of the loss is the value on the surface, right? And then you are looking for the choice of weights that give you minimum loss, right? So that you are looking for this point, right? So the value of the function, the surface, what the height is, say this is some surface like this, right? If you get to this particular point, there is one particular height from the ground, right? That height is the value of your function, value of your loss, right? This is the minimum loss you can get out of your model, right? And the point that is just calculating this value, that point in the W space, this is the choice of your weights. So you should go in your neural network, put your first weight to be W1, your second weight to be W2, exactly this value, right? To get that particular loss that you're looking for. Clear? Yeah, if you are at the local minimum, then you are not doing perfect.
Yeah,
but
what if it's a surface like any other point, but it's a slope? So what is
you mean it's a plane?
Yeah.
It's
so
not. I mean, this is not going to happen because if it wants to be plane, then you have extremely simple model. But if you are just thinking about optimization, like not about practical neural network with lost surface, you are just thinking about any surface, right? Then this is a valid question that you have just a plane, right? And what is the minimum point? This is your question, right?
No. You just mentioned the height.
Yes.
The loss.
Yes.
The loss.
Yes.
What if it's not at the minimum, it's at somewhere else?
Some other point.
There are so many heights.
Yes, exactly. I mean, if, for example, say this point is 1, 1. Like W1 is 1, W2 is 1. Okay? But this other point, let's say you come here, this other point is 2, 1. Okay? If you put the weights inside your neural network to be 2, 1, then the loss that you are going to achieve is going to be that second point. If you put them 1, 1, then the loss that you're going to get is going to be that minimum value. Now, what you are looking for, you want to have the weights which give you smaller loss, right? So you're going to put it 1, 1, right? But if you change it, randomly choose it, say you randomly put it 3, 4, right? Then you come here, you would say, okay, here is 3, here is 4, this is the value of the loss, right? That's it. This is telling you for any combination of weights, what is the loss. Yeah? No. Questions? No question? Great. So if you got no question, then let's see if we have the same property as before. So in the one-dimensional case, what did we say? We say just look at the derivative, interpret its sign as the direction. Then that direction is the direction that the function is increasing, right? Now, what about the multidimensional case? Well, if you think about a surface, then there is no single direction that the surface is increasing, right? So if you are going up on a hill, then you can move like directly on the steepest direction, right? And you are increasing in height. You can just move with a bit of tilt, right? You're still increasing, but not as fast as before, right? So there is no single direction that the function is increasing anymore. In the one-dimensional case, the story was simple. We had only two directions, right? Forward, backward. And then one of them is increasing, the other one is decreasing, right? But now when you are in a multidimensional space, like even in two-dimensional space, you have lots of directions where the surface is increasing, lots of directions where the surface is decreasing, right? Now, the key point here is that you can show this. This is not very hard, that your gradient is always perpendicular to the contour of your surface. What is a contour? Think about a hill, okay? And now I want to think about any point that is at this height, right? What I'm going to do, I'm going to cut the surface, right? And then what I see if I look from above, I'm going to see a circle, for example, right? So that is the contour. All of the points on the contour are at the same height. The value of the function on them is the same, right? Now, this red curve that you see here is the contour of the function. So I got the function. I said, for example, I want to look at height 10. So I went on the third axis, axis y. I went to point 10, and then I just did a cut, right? Then I went up and looked at the surface, right? I saw a contour, right? That is that contour. And when I look from above, I still see my direction of move, right, W, and I can see also my gradient because they lie on the W surface, right? Just look at this guy. If I cut it and I go up from above, I still see W and gradients, right? Correct? So this is what I'm showing you here. And what you can prove, this is not hard to prove it, you can prove that that gradient that you are plotting is orthogonal to that contour. Like if you just draw the tangent line on the contour at that point, this is orthogonal to that guy. Right? Everybody's cool? Okay. So if that is the case, now if I want to know what's going to happen, like I can, on this particular point, I can move in any direction, right? In any direction. Now, say I choose one specific direction, dw, like this, right? If I want to know how much my function is going to change, what should I do? I can write it down in this form. I can say this is the gradient, right? This gradient is going to get multiplied with this direction, dw, right? Inner product. This is going to give me the change in the value of my function, right? Everybody's cool? Right? Now, since everything is two-dimensional here, I can just use basic formulation, right? You can do it for any number of dimensions, but right now it's quite intuitive, right? Say the angle between these two is theta, then going to be the length of this guy, dw, times length of the gradient, times the cosine of the angle between them, right? This is the inner product. This is another formulation for inner product, right? Okay. Now, what I can say, I could just write down, keep this formulation here, and what I say, I would say, okay, I'm just thinking about the direction of my move. I am not thinking about my step size. So I think that no matter which direction I'm moving, I'm always taking a tiny step epsilon, okay? So it's like I stop here, I would say here or here or here, like this, right? So it's like I plot a circle with my leg, okay? Okay, now if I do that, so I have this guy set to epsilon. Now my question is which direction should I choose, which theta I should choose to have the most increase in my function. Can you tell me what it should be? Just look at this guy here. If I put this blue dw, I put this norm to be epsilon. So this is something constant. The gradient I have computed again. The norm of it is constant, right? The only thing that could change the value of the increase here is the angle between my direction and the direction of the gradient. What should I put this angle to be to increase maximally? 0, right? So if I put the angle to be 0, then that inner product is going to be the largest value ever, right? So what do you conclude? If you have a multidimensional function, at any point, you can compute the gradient, right? That gradient gives you a direction. What happens if you move in that direction? Your function is going to increase, of course, but not only increasing, it's going to increase with the steepest slope, right? So this is what you call it the steepest direction, right? And this is always given by your gradient. Clear? Now, just a question before. If you want to minimize it, so you want to just decrease it as steep as possible, right? What is that direction? Totally opposite, right? Instead of going right up, just go right down, right? So if you put theta to be pi, then it's basically the negative direction of the gradient. And then this is the direction that your function is going to decrease as steep as possible, right? And this is the thing that we want, right? We wanted to look at one point, then know the direction where the function is decreasing. And the gradient is giving us that direction. Not only that direction, but the direction that is the best, right? So the direction that the function is decreasing with the highest speed, right? So the best choice for mu is to just set it to be minus the gradient, right? Yes, you had a question. It's always the case. Decrease your function, right? Following the gradient, sorry, increase your function, right?
Yeah, I mean, if a contour is like facing negative direction, would that be opposite way?
No.
So it's always increasing?
Always increasing, right? The gradient, I mean, the case that you said, the gradient itself, after computing, it's going to get reversed. Yeah, but you always are, I mean, gradient direction is always the direction that you are increasing. One thing that I see many students have like in mind, they think like gradient descent idea is working sometimes, it doesn't work sometimes. No, it works always. Gradient direction is the right direction to increase maximum, and the negative is the direction that you decrease. The issues start when you want to, for example, move step by that, right? Because you can just pass some minimum, right? This is one thing that could happen. The other thing is that not all the functions all the time have gradients, right? There are crazy functions who are discontinuous, who have edges, and they do not have gradients, right? And then in that situation, you might get into trouble because you cannot compute that direction, right? But if you have a smooth function, it doesn't matter if the function looks like this. At any point, if you move in the direction of the gradient, you're going to get higher, right? But like if the function is crazy, varying, changing in the space, then you don't know how much small should be your step size, right? Because you can just, it could be very fast that you move a tiny bit and then you pass one maximum, you get into another point. That is the practical issue. But the fact that the gradient is moving us towards the maximum increasing direction, that is a kind of established fact. Questions? So, moral of the story, just if you want to decrease your function maximally at every single point, the thing is that you need to just move in the negative direction of the gradient, right? And this is going to conclude basically the gradient descent algorithm. Now, if we have a multidimensional function, when is the gradient minimum, 0, sorry? Maximum, minimum, and actually we call that saddle point, right? Because you can have a different story here. So you could have a maximum, right? And you can again do the same thing as we did for one-dimensional vectors, functions. I am not going to do that again for you because it has a bit of more, it needs a bit of more imagination. But you can simply take it from my side. And between us, we are never going to check it, okay? So this is just as a kind of extra information. But the key point is that like the second order derivative, which is like the Hessian matrix, is going to be always negative definite when you are at the maximum, right? The gradient is going to be 0. Like the slope in every direction is 0. And the Hessian matrix, it means that the matrix containing all possible second order derivative, this is going to be negative definite. So if you don't know what is negative definite, you can check it. But as I said, this is not important at all because this is not, we're not going to do second order algorithm, so this is just a kind of extra information. Now, you could get into the minimum as well, and then again on the minimum, when you think of a surface, the point where it is minimum, then at that point the slope in all directions is 0, right? So the gradient is going to be 0. Every single entry in it is 0, right? And the second order derivative, which is Hessian matrix again here, is going to be positive definite now. Okay? And now, yeah? No, it's different from Jacobian. I'm going to show it in another slide. Yeah, it's the second order. Like you have a function of W1, W2, right? Then how many second order derivatives you have? Second order derivative with respect to W1, 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 W2, W2, W1, W2, W2. It's a matrix, right? That's that matrix. But Jacobian is when you have, it's still a gradient, but you have a vector output. We have it in a couple of lectures, yeah. Yes? Yes?
Wouldn't it make sense to choose my step based on how fast the light changes?
Yes, we actually do it. I'm going to explain it later, so no worries about that. But we're going to get into that point as well. But just a bit of a spoil. If you keep it constant, the amplitude of the gradient itself is going to tune it, right? But we have better approaches to do that as well. Yes, you had no question? Okay. So, questions? No question? Okay, so the third kind of points that you might have is what we call its saddle point, right? And the saddle point happens in multidimensional functions. Why? Because just think about one function. A function, when you think of a surface, you could have a minimum if you move in this direction, right? The function gets minimum. But when you move in this direction, you are getting maximum, right? So saddle point is the point where you have minimum in some directions and maximum in some other directions, right? And why we call it saddle point? Because just think about the saddle on a horse, right? The one which you sit on it, right? The direction that you sit on it is maximized, right? But the direction which is orthogonal to that has a minimum at that point, right? So the center of that saddle is the point where you have the gradient again 0, the slope of every tangent line is 0, but when you move in one direction, your function increases. If you move in another direction, your function decreases. This is the saddle point, and then when you compute the Hessian matrix, this is neither negative nor positive definite, okay? And this is where you don't have actually the point that you want. Questions? No question? Okay, great. So this is the Hessian matrix that I told you. So if you have a function f of w, then this w can have n different variables. Then you can take the second derivative by considering those two derivatives that you are taking the derivative with respect to, those two variables, to be any possible pair, right? So you have second derivative with respect to w1, 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 w2, w1, w3, still w1, wn. This is the first line. Again, you will start with w2. It's going to be w2, w1, w2, w2, and so on till n. So it's going to be a matrix, right? And the dimension is obvious, n by n, right? But as I said, we're not going to use it. I mean, we're going to have a hard time just computing gradients, so we cannot compute this guy anymore. Okay? So, yeah. That's it. So moral of the story, just to wrap up everything. So the best way to update at every single point w0 is just to move in the direction where the function reduces maximally, and that is the negative direction of the gradient. So this means that I can write down my algorithm in this form, and this is the most generic form of the gradient descent, at the same time the most basic form. So what is it? I start from one particular point w0, and then I start updating. So at point w0, I'm going to compute the gradient at that point, exactly w0, right? I find the direction of the gradient. I move in the negative direction, right? Minus gradient. And I do it with one tiny step, right? This eta is a tiniest step, which is helping me that I am not going to overshoot, right? And this is what we call it typically learning rate, right? So we are starting from one point, then we compute the gradient, and then you get that direction. So you multiply with this step size, you get your new weight, right? Now that you have your new weight, you check your loss function. If it is just different from the previous one, you keep on doing it. Why? Because you say that I am at one point, and I am going to decrease, right? And I keep doing it till I get close to the minimum. When I am at the minimum, what's going to happen to that gradient? It's going to be 0, right? This means that the W is not getting updated anymore. Every iteration, you have the same W, right? And then what's going to happen to this delta, the difference? If I am arriving at the minimum, okay, I again say get into the loop, and I compute the gradient. The gradient is going to be 0 because I am at the minimum, right? Now, the new weight that I am computing is the previous weight minus 0, which is the previous weight, right? So what is the difference between my loss function in the previous iteration and this iteration? Is 0, so delta is going to be 0. The loop is going to end, right? So this guy is not working because the direction is the direction that I am decreasing, 1. Secondly, it's going to stop when I arrive at the minimum, right? So this is the gradient descent algorithm, and this eta here is what we call it. We call it learning rate, okay? Now, that's pretty much this about the gradient descent. Now, there are a few things that I want to mention here. In the next lecture, we're going to talk about this. The first one is that I want to convince you that when you use gradient descent, you're not going to get trapped at any other point like a maximum or saddle point. That is not going to happen. This is very easy to see it, but we'll try it once together, okay? Once we have it, we end up with the fact that if we use a gradient descent, at the end of the day, we're going to end up with one minimum, right? And that minimum is a local minimum, right? And that's fine for us. Then the question is that when we can have this local minimum exactly the global minimum. Well, if the function is convex, that happens. If it's not, that does not happen, but we can do nothing about this, okay? And that's it. The gradient descent is here. We're going to leave it. We assume that we can use it. Then later on in chapter 3, we get back again to this one. After we try a bit of training, we understand what are the bottlenecks with the basic gradient descent, and we try to develop the new algorithm, which is eventually the momentum. Atom, the one which most of you use it. We understand how they work, but again, all of them are a kind of modified version of this algorithm, okay? Questions? No questions?